Hello everyone, I hope you all are doing well. In this video we are going to solve question number 4 from chapter number 4 of solid state physics by Kittel. Okay, this is the chapter name for note 1, crystal vibrations. So in this video we are going to solve question number 4. I have already uploaded the video before, but the language of instruction was Urdu, and most of my viewers, I have noticed that they don't understand those languages. That is why I'm shifting my content to English as the main language of instruction. So don't worry, the rest of all the videos that will be uploaded in this channel will be in English, until and unless it is particularly requested to upload it in other languages. Okay, additionally, if you have any problems or if you are finding difficulty in finding out the solutions to some problems, then you can simply comment. I will direct you to the solution of those problems as soon as possible. Let's understand the problem first and then we'll dive into the solution, because understanding the problem is the crucial part in solving the problem. Okay, we should first know what the problem wants us to solve. Okay, we suppose that the interplanar force constant Cp, P is in subscript of C, between planes S and S plus P is of the form Cp equals capital A sine P naught A divided by PA. Here we have interplanar force constant. Let me write it into the paper, okay, which is the given data C, and it is small p, that is equals to capital A, which is a constant, as it will be mentioned in the problem later on, divided by PA. All right, here capital A and K naught are constants. Here we have capital A and this K naught, these two are the constants. P runs over all integers. P is a number, okay, that shows the number of plane actually. Okay, for this particular problem, P is showing the number of plane that we are considering, and it is a variable, hence there could be the first plane, second plane, third plane, or pth plane. Okay, and it runs over all integers. It couldn't be negative. It could be the first plane, second plane, third plane, fourth plane. All right, it couldn't be a fractional number because we are counting the planes. Okay, and there couldn't be a thing like a half plane. Okay, we are, for example, counting it. There could be a one plane. For example, these are some of the planes, and if you're counting, it will allocate one number to this, 2 to this, 3 to this, 4 to this. It is just like as if we are counting something. For example, how many planes are there, and we'll say, for example, we have 2 planes, 3 planes, 4 planes. Such a form is expected in metals. We expect that form of force constant in metals. It is experimentally verified. It was experimentally detected, and using this form of force constant and equation 16a, the 16a equation is basically available in book. You can refer to that article where they told you people the expression for force constant of metal lattice. So it is 2 by capital M. M is the mass of the atom of which the lattice is made up of. Summation runs over P, which is greater than 0. We'll consider the positive ones because there is nothing like a negative one plane. Okay, we are counting the planes. For example, it's the first plane, second plane, third plane, fourth plane. Just like for example, there are some humans, you are counting them. This is the first in line, this is second in line, third in line. We cannot allocate negative numbers because it doesn't make sense. So we have summation that runs from P greater than 0, C P 1 minus cos P K A. Okay, this is a simply dispersion relation for the metal lattice. Okay, this is typically used in metals. So this is the equation number 16a that they are referring, and it is available in the article of solid state physics by Kittel. Okay, you can simply refer to the article where you will find that equation. So we'll use this expression and this dispersion relation To find an expression for omega square, we have to find out an expression for omega square using this force constant, and also for partial omega square by partial k. Okay, we have to find out the partial derivative of omega square with respect to capital K, and we have to prove that this partial derivative is infinite when capital K is equals to k naught. We have to prove that, and there's a plot of omega square versus k, or of omega versus k has a vertical tangent at k naught. There is a kink at k naught in the phonon dispersion relation omega of k. So we have to prove that if you plot omega square versus k, then we'll find out a vertical tangent at k naught. Vertical tangent means a point of infinity. Okay, so what we have to do in this problem is to find out the dispersion relation for this problem, okay, using this Cp and equation 16a, and after that we have to find out the partial derivative with respect to k of that dispersion relation, and after that we have to prove that at k is equals to k naught, partial derivative becomes infinite, and then we have to draw a rough plot to show that kink at k equals k naught. Okay, so these are the 2 or 3 tasks that we have to do in this problem, and it's very easy problem. It will be done in a few simple steps. So let's start the problem now. Now we have this dispersion relation. We know that the solution starts. We know that the dispersion relation for the metals is typically given by this expression. Okay, I wrote these two things in rough work. Okay, so this is the main thing that is happening here, and let us putting given expression for Cp, we get this thing. Cp equals capital A sine pka pk naught a. Okay, this is the theta of sine divided by pa. Okay, pa is divided by the whole expression. It is not in the angle, keep that in mind. And this is the Cp value into 1 minus cos pka. Okay, the summation, all those things will come inside the summation which has p in them. Okay, capital A and small a are independent of p, so they will come out of the summation expression. Okay, and we'll be left with sine p k naught a. Okay, this is angle, and 1 minus cos p k a. This is the expression for omega square. It's divided by p. So this is the expression that we had to calculate in this problem, and we simply found it by plugging the value of Cp into this expression that they highlighted, that they mentioned in the problem. Now we need to calculate partial omega square by partial k, and it will be simply calculated by taking the derivative of this expression with respect to k, and the derivative will be a partial derivative as they mentioned it. So let me do it now. Now I'm gonna apply the operator. Since these are constants, they will come out of the operator. We will simply apply it on these expressions. Here we can see that the partial derivative is with respect to capital K, and it will be applied only on those expressions which has K in them. Okay, and there is only one expression here which has capital K in here. K naught is a constant as mentioned in the problem statement, so rest of all the values will remain unaffected. It will be only applied on this expression which has capital K in it. So let me apply that operator right here on this expression inside the summation. So next step is to multiply that operator inside this expression. We can see here there are the two expressions. So partial by partial k on 1 minus partial by partial k on cos p k k a. Okay, since it's constant, its derivative will be 0. Okay, its derivative is 0 minus derivative of cos of theta. Derivative of cos theta, let's say with respect to x, to have some difference, will be equals to minus sine theta. Okay, this cos theta will change into minus sine theta dot derivative of angle with respect to the operator. Okay, the original operator will be applied on the theta also. So we'll have this minus is already present here, minus sine theta. Theta is pka. Okay, dot this operator will be applied on theta also. Theta is pka. Okay, these are the fundamental rules that we should remember and should understand at first place. And if you have any difficulty in understanding how differentiation rules and how integration rules works, then you can request me. I'll upload that series of videos where I'll make you people understand how to apply several rules in a general way, which could be applied in every situation you come across. Okay, so we have partial derivative, and it's the property of partial derivatives then that it is only applied on those functions that have the similar variable on which like that derivative is in. Okay, for example, it is applied with respect to k, so it will be applied on k terms only. P and a will be treated as constant and they will come out of the partial derivative, and partial k by partial k is 1, so it's 1 here and pa is left. Hence it's pa times pa, I'm writing it on the left side, sine pka. This p and p cancels, this a and this a cancels out, and we are left with 2 capital A capital M, p greater than 0, sine p k naught a, sine p k a as partial omega square by partial k. This is the second thing that we needed to calculate. Okay, now we need to prove that what happens at k is equals to k naught. We have to put simply k equals k naught here. We need to prove that in this situation at k is equals to k naught. Okay, in this side you will write it like that you are putting actually k equals k naught because k is appearing that side of equation too. So this remains unaffected, but here in this expression we'll put it here, so it will become sine square p cannot a because the angles are same, and this is 2 capital A divided by capital M summation p greater than 0 sine square p k naught a. Now to simplify it and get it to a form that will give us some information, we will put that identity here, that if we have sine theta then we can write it as 1 minus cos 2 theta by 2. Okay, this is a double angle identity and we'll use it. So sine Theta is pk naught a, so we'll replace pk naught a with theta here. So 1 minus cos 2 into theta, which is pk naught a divided by 2. This 2 will come out of the integral, summation. To pk naught a. Now summation, this 2 and 2 cancels out, capital A by capital M. This summation will appear with this expression and also with this expression, because we have two expression being subtracted and we have this common, so it will be multiplied with this and this, so it will appear with this and this expression too. I hope you understand what I'm trying to say. Because the summation was common to both of these expressions, so it will appear with both of these expressions if we wish to write separately. Now let me write the summation in its upper limit, which is infinity, which is not usually mentioned because of obvious reasons. Lower limit is mentioned here, upper limit is infinity, positive infinity, and this summation creates a problem as this expression diverges. Not this one, but this one mainly diverges here. So if the infinity is being subtracted from any number being multiplied or added, the result will be infinity also. So partial omega square by partial k at k equals k naught equals infinity. Okay, which means we will get a vertical tangent. We'll get a vertical tangent at capital K equals k naught in omega square versus k graph. Okay, how we can say this? Because we have the expression omega square, we had the expression of omega square. Okay, and if we want to find out the tangent to omega square, okay, so in order to find that tangent, we do it by finding out its derivative with respect to the variable, which is capital K here, because we are wishing to find out the relationship between omega square and k, and that is why we'll find out the tangent to omega square versus k, and that tangent at particular position k equals k naught. We want to find out the tangent to this expression at k is equals to k naught, and we can do it by finding out its partial derivative or derivative. Simply derivative means slope, finding out the slope. So if you want to find out the tangent, you can do it by finding out its slope or derivative. So we found the derivative of omega square with respect to the variable, okay, concerned variable, which is k, and finding it gave us this expression. Yeah, this expression. And since we wanted to find out its tangent specifically at k equals k naught, so we inserted the value right into this expression, and solving it gives infinity, which means that the tangent to omega square versus k graph at k equals k naught goes to infinity, or the tangent is vertical. Okay, so we can express this thing in graph in this way. Let's say we have omega square here in y-axis and k on x-axis, and this is origin. Okay, so we can see here that the determining factor here is 1 minus cos pka. This will determine the value of omega square. Its maximum and minimum values would be decided based on this expression, because k is a variable, main variable, that we are actually drawing on the plot. Okay, omega square and k are the main functions, and k only appears in this expression. So this is the determining function that determines the maximum and minimum value of omega square. And if we see the ranges of cos function, then we have these ranges -1 to +1. Okay, so if cos pka is equals to 1, then we'll get 1 minus 1, which is 0, and the whole expression will become 0. So omega square starts with 0. It will be a sinusoidally varying function, but at k equals k naught, let's say this is the point where k is equals to k naught. Okay, we will get a vertical line here, a sharp vertical line here. Okay, and this shows the discontinuity in the graph. And after k is equals to k naught, right after k is equals to k naught, it will continue to vary as it used to, but at specifically k is equals to k naught, it will show a point of discontinuity where the graph will have a kink, while the all rest of the all points will not be discontinuous, and there will be a continuous graph, but at this particular point it will be discontinued. So that is something that we needed to find out, and we did it. I hope you understand it. Like, share and subscribe, and to tell me if you have any other problem that you want me to upload. Take care. Goodbye.